In this example, we try to prove or disprove a statement using the techniques that we have learnt. Consider the statement: for all natural numbers n which is prime, there exist integers a and b such that n equals a squared plus b squared. It means that for any prime number n, I can always write n as the sum of two squares. This seems too strong of a statement to be true. Let's look at the negation to have a different view of the statement. It is: there is a positive integer n which is prime, such that for all integers a and b, n is not equal to a squared plus b squared. This means that we have to find one prime number n such that n is not a sum of two squares. This seems plausible, so let's try to prove it. The smallest prime number is 2. Can we write 2 as a squared plus b squared? Yes, because 2 is 1 squared plus 1 squared. So let's look at the next prime, 3. Can we write 3 equals a squared plus b squared? Let's assume that we can do so. Since we know that a squared is non-negative and b squared is non-negative, for any integers a and b, we must have a squared is less than or equal to 3. In fact, b squared is also less than or equal to 3, but we just need to consider a squared. Since a is an integer, we must have a squared equals 0 or a squared equals 1. Let's consider each case. If a squared equals 0, then b squared equals 3. So b equals plus or minus square root of 3, which is irrational, a contradiction. If a squared equals 1, then b squared equals 2, so b equals plus or minus square root of 2, again irrational. Since we have reached a contradiction in each case, our assumption that 3 equals a squared plus b squared is wrong. In other words, 3 is not equal to a squared plus b squared for all integers a and b. So the statement is false, where 3 is a counterexample.